All right, my friends, let's take a look. So f of x equaling cosine of x. Let me kind of line things up over here. Oops. So we're looking for a fourth degree Taylor polynomial. So we'll need up to 4 derivatives. So f prime of x be the opposite of sine. F double prime be the opposite of cosine. F triple prime, I wish I had written smaller, would be positive sine of x. And then, let me leave some space here. The fourth derivative in terms of x would be cosine again. And you can see some evidence of like a cyclic pattern, because if somebody asked me what's the 5th, 6th, 7th, I would just kind of like read off these derivatives. So you can definitely see some like the cycle that you could take advantage of if they asked you for the, if they're horrible and asked you for the 11th degree Taylor polynomial, you wouldn't have to work too hard because you could take advantage of this cycle that we see here. Okay, now we're supposed to have this centered at 0. So let's do f of 0. So let's see, cosine of 0 is 1. F prime of 0, sine of 0 is 0. F double prime of 0 would be -1. F triple prime of 0 would be 0. And then the fourth derivative evaluated at 0 would be 1 again. Okay, so what does that mean? It means cosine of x can be approximated with, okay, so now my friends, let's just make sure we know what we're doing here. Here's the plan. We're going back to this right here. It's just this time f of x is cosine, right? Okay, so we're going to do f of 0, which is 1, plus f prime of 0, which is 0, times x divided by 1 factorial, plus f double prime of 0, which was -1, times x squared divided by 2 factorial, plus f triple prime of 0, which was 0, times x cubed over 3 factorial, plus the fourth derivative of f evaluated at 0, which was 1, times x to the 4th over 4 factorial. And they just asked us for that, so we would stop there, okay? Now, before moving on, I would simplify what I have, and maybe you already simplified, but just to kind of show how I'm using that formula up there, I wanted to show the pre-simplified version. So if I simplify this, then I end up with 1. This is 0, so I'd end up with, oops, goodness gracious. I'd end up with 1 minus x squared over 2, or 2 factorial. This would vanish as well, and then we'd have plus x to the 4th over 4 factorial. There we go. And you could see that cosine of x, as you add terms, it kind of has its own pattern, which we will talk about in the future. But for now, this was the ideal answer for part A. So congratulations if you got it. Now, the next couple parts, I'm going to have a part B and a part C to this problem. And when we get to part C, it's going to be very, very, very AP prep style type stuff. So for part B, use your polynomial from part A to estimate the following. So cosine of 1. So cosine of 1, if you use your polynomial that you got, you would just plug 1 in where all the x's are. So it would look like this: 1 minus 1 squared over 2 factorial, which is 1/2, plus 1 to the 4th over 4 factorial, which would be 1 over 24. And then if we were to simplify that, what would that be? 24 minus 12 plus 1. So that would be 13 over 24. So we would say cosine of 1 radian is approximately 13 over 24. Okay, and then cosine of 2 radians, you would just take your answer over here and plug a 2 in for all the x's. So you'd have 1 minus 2 squared over 2 factorial, which would be 2, plus 2 to the 4th, or 16 over 4 factorial, which would be 4 over 3 times 2, which would be 2 over 3, I think 2/3. And then when we group this together, let's see, -1 plus 2/3, is that -1/3? I think it's -1/3. Now make sure you don't say exactly equal to -1/3. That will make you look like you are very lost and confused. Okay, hopefully you're feeling okay about what we're doing here. Let's go back to the graphical reasoning and talk about kind of what we found here and what that means as far as the graph goes. All right, my friends, let's see what I have here. I have the graph in blue of f of x equaling cosine of x, and then I've got, you can see at the bottom, I could change where I have things centered. So I'm going to keep this centered at 0. We'll talk about not centering things at 0 in a little while. So I've got this centered at 0, and I wanted to kind of show the different Maclaurin polynomials that you could have. So the current horizontal red line is the 0-degree Taylor polynomial, which is a super great approximation for cosine at any multiple of 2 pi. Otherwise, it's horrid, right? But if I was to bump this up by 1, I wonder if after the work that you've done, I hope it makes sense. When I bump my n value up to 1, nothing happened. It's still that horizontal line. But that's because that first derivative, when you evaluated it at 0, it was 0. So that first degree term was 0. So that's why you see no change. But then when I bump it up to 2, you will see a change because you didn't get 0 for your second derivative. Yeah, so let's bump it up, and then when you bump it up to 3, will you see a change? You sure will not, because your third derivative was 0, remember that? And then fourth degree, there you go. Now you see a change like that. So, all right, so now let's talk about what, so this red graph is the polynomial that you found in part A of that last example. And then let's talk about in part B what you found. So, so I hope it makes sense. Pi here, pi, which I can't draw on the screen, I guess, but pi is over here, and pi is about 3.14. So, so 1 radian would be maybe about here, right? So which one do you guys think is closer to the real thing? What we got for cosine of 1 when we plugged 1 into the polynomial, or what we got when we plugged in 2? So 2 would maybe be, I don't know, about here. So which one is closer to the real thing? What we got in part B for cosine of 1, which would have been over here, or what we got, for cosine of 2. I hope it makes sense that cosine of 1 would be a lot more accurate. And how come? Because you centered it at 0. And so the closer you are to the number you centered it at, the more accuracy you can rely on. The farther away you get from where you centered your polynomial at, the worse, the worse off you'll be. So hopefully that makes sense. And then we'll have a part C to it. But I did, when we're here, I wanted to talk with you about the idea of centering these things at different values. So for example, if I was to center things at, let's bump this over, if I was to center this at pi instead of at 0, first of all, why would I want to do that? For a couple reasons. Sometimes you can't center things at 0 because of domain restrictions. We'll show an example like that. And then sometimes let's say you wanted to be able to plug in something that's not so close to 0. You wanted to plug in things that are closer to pi. Then you might choose to center it at pi instead, because it's more accurate around values that are close to 3.14. So Anyway, but you could center these things anywhere. They, you know, the way they look definitely changes. So like here, if I was to center it at about, whoops, what is that? Move that a little to the left. Oops, come on, move. Okay, there. Like if I was to center it at 3 pi over 2, you know, the way things would fall would be a lot different, but you'd still end up with the same concept of a polynomial that's kind of hugging the curve that you're trying to model tighter and tighter, but tightest, of course, at wherever you centered it. So anyway, for now, we're still working on centering things at 0. And I do have a part C for you. So let's get back to part. All right, my friends. So for part C, I'd like for you to think about how is it that we could know that the actual cosine of 1 is within 1/700th of what we got when we plugged 1 into our 4th degree Taylor polynomial up above. So basically, how do we know that the actual true perfect value of cosine of 1, how do we know that it is within 1/700th of that 13 over 24 that we got up there when we plugged 1 into that 4th degree polynomial? Give it some thought. Check in with me in the next video.